P block elements, group 16, oxygen family, also known as chalcogens. These elements are ore forming, that is why they are known as chalcogens. Oxides and sulfides are common ores. These elements include oxygen, sulfur, selenium, tellurium, and polonium. Of these, the first two elements are non-metals, the next two metalloids, and the last one, polonium, is a metal. Oxygen exists as a diatomic molecule, whereas sulfur exists as a polyatomic S8 molecule. Some physical properties: atomic size, density, melting point, and boiling point, these increase down the group. Polonium has a lesser melting point and boiling point due to inert pair effect. Ionization potential, electronegativity, and electron affinity decrease down the group. Non-metallic nature decreases and metallic nature increases down the group. Let us see these properties one by one. The table shows melting and boiling points of these elements. As you can see, they are increasing down the group. It is because of the increased van der Waals force of attraction as atomic radii increases from oxygen to polonium. This graph shows the trend of melting point and boiling point for these elements. As you can see here, polonium has lesser melting point and boiling point as compared to tellurium. As told earlier, it is because of inert pair effect. Covalent radius and ionic radius, it increases down the group due to increase in number of shells. Ionization enthalpy decreases down the group. It is due to increase in size. The table shows various properties and their values. Here one thing is to be noticed, that though oxygen is more electronegative than sulfur, you can see the value here, 3.5 for oxygen and 2.44 for sulfur. But the negative value of electron gain enthalpy is lesser negative for oxygen as compared to that of sulfur. It is because of small size of oxygen. As it gains the extra electron, there occur inter-electronic repulsions, and some of the energy is used to overcome these repulsions. Anomalous behavior of oxygen. Oxygen, being the first element of the group, has different properties. It is because of its small size, its high electronegativity, and absence of vacant d orbitals. In physical state, oxygen is a gas, whereas other members are solid. Atomicity of oxygen is 2, whereas others are polyatomic. Magnetic behavior. Oxygen is paramagnetic due to presence of unpaired electrons, whereas other elements are diamagnetic. Oxidation states. The general oxidation state for oxygen is -2 in most of the compounds, whereas rest of the elements can exhibit positive oxidation states also. Due to higher value of electronegativity, oxygen is capable of forming hydrogen bonds, whereas other elements cannot form hydrogen bonds. The nature of the compounds of oxygen are more ionic as compared to those of other elements. Oxygen is capable of forming p-pi multiple bonds with elements of comparable sizes, and this tendency decreases down the group. The hydrides of oxygen, that is water, is liquid at room temperature, though other hydrides are gases. Oxidation states. Except oxygen, chalcogens exhibit -2, +2, +4, +6 oxidation states, means they can show positive oxidation states as well, whereas the common oxidation state for oxygen is -2, though it can show -1 oxidation state in peroxides, +1 in O2F2 and +2 in OF2. Oxygen is a powerful oxidizing agent and H2Se and H2Te are reducing agents. Sulfur, selenium and tellurium are mostly exist in positive oxidation states, +4 in SF4 SO2 H2SO3 and +6 in SF6 SO3 H2SO4. About the hydrides, water is liquid while other hydrides are colorless, foul-smelling toxic gases. Bond length increases down the group, bond energy decreases down the group, volatile nature decreases. Acidic strength and reducing strength increases from H2O to H2PO. They both depend on thermal stability, which decreases down the group due to increase in size of atom. This table shows the values of different properties of these hydrides. Here you can see melting and boiling point for water. These two values are higher than that of H2S, though they increase further for other elements. It is because water can form oxygen can form hydrogen bonds in water, though there is no hydrogen bonding in other hydrides. Halides have a general formula M2X2, MX2, MX4 and MX6. Hexahalides are like SF6, ACF6, TEF6. Tetrahalides, except oxygen, all elements of form tetrahalides of chalcogens. Dihalides, except selenium, all can form dihalides. HCl2 has foul smell. Figure is mustard gas having formula SCH2CH2Cl whole twice. Monohalides, S2Cl2 is toxic yellow liquid. Its structure is open book-like and has an angle of 104 degree. Then about hexahalides. Sulfur reacts readily with all the halogens except iodine. It ignites spontaneously in fluorine and burns brightly to give hexafluoride. The structure of SF6 is shown here. It is a colorless, tasteless, odorless, non-toxic, thermally stable and insoluble compound. Despite the +6 oxidation state of sulfur, it is not a good oxidizing agent. The reason being its inertness is due to presence of sterically protected sulfur atom. Now the oxides. Chalcogens can form dioxides and trioxide. Acidic nature decreases from oxides of sulfur to polonium. Dioxides dissolve in water to form us acids, whereas trioxides form ic acids. As shown here, SO2 form H2SO3, which is sulfurous acid, whereas SO3 form H2SO4, which is sulfuric acid. Some chemical properties are listed here. The product of reaction with O2, the oxides form are shown here. These type of oxides, they range from acidic to basic. The first two are acidic, then TeO2 amphoteric and POO2 is basic. Then with nitrogen, only oxygen can form oxides. Others cannot form. With halogens, the compounds are shown as told earlier. With hydrogen, they form hydrides. Then coming to oxygen, the first element of the group, it exists in two allotropic forms, the oxygen diatomic molecule and ozone, its triatomic form. Oxygen is prepared by thermal decomposition of oxygen-rich compounds using MnO2 as catalyst. Here the reaction is shown. KClO3 on heating forms O2 and KCl in presence of MnO2. Similar is the case for KNO3. Commercial preparation of oxygen involves electrolysis of acidified water and fractional distillation of liquid air. The diagrams are shown here. Properties of oxygen. Oxygen is a colorless gas without smell and taste. It is slightly heavier than air. It is sparingly soluble in water, and this helps for aquatic life to survive in water. It is difficult to liquefy, boiling point 90.2 Kelvin, and the liquid is pale blue in color and is appreciably magnetic. At still lower temperatures, light blue solid oxygen is obtained, which has a melting point of 54.4 Kelvin. Different species of oxygen which exist. The oxygen diatomic molecule as shown, the superoxide O2 minus anion, the peroxide anion O2 2 minus, then hydrogen peroxide H2O2, hydroxyl free radical OH free radical, hydroxyl ion OH minus ion. Reactions of oxygen. Some of the reactions of oxygen with metals and non-metals are shown here. Oxides are formed in both the cases, though metallic oxides are basic in nature, whereas non-metallic oxides are acidic in nature. There are some neutral and amphoteric oxides also, which will be discussed later. Some compounds are catalytically oxidized, like SO2 to SO3, HCl to Cl2 in presence of catalyst. Types of oxides, as told earlier, acidic oxides are non-metallic oxide, like SO2 forms sulfurous acid on dissolving in water. Then basic oxides are metallic oxides, like Na2O forms NaOH, they form alkalis on dissolving in water. K2O forms KOH, CaO forms CaOH whole twice. Then some amphoteric oxides. Amphoteric oxides of aluminium oxide is shown here. It reacts with acid as well as with base to give products, salt and water. The neutral oxides, these oxides are neither acidic nor basic. Examples are CO, NO and N2O. Ozone, as told earlier, is a triatomic molecule. The resonating structures of ozone are shown here. The position of double bond changes in the two. It is an allotrope of oxygen, that is much less stable than the diatomic allotrope O2. Ozone is formed from dioxygen by the action of ultraviolet light and also atmospheric electrical discharges. In total, ozone makes up only 0.6 parts per million of the atmosphere. The formation is shown here. In presence of ultraviolet radiation, oxygen molecule breaks into oxygen atoms as shown. Then this oxygen atom combines with molecular oxygen to form ozone molecule. Properties of ozone. Ozone is a powerful oxidizing agent, far stronger than O2. It is also unstable at high concentrations. Ozone also oxidizes nitric oxide to nitrogen dioxide. Ozone oxidizes sulfides to sulfates, like lead sulfide to lead sulfate. Sulfur. Sulfur has more allotropic forms than any other element. The figures are shown here. It exists as S2, S, S2, S6, S8 and Sn also. The two important allotropes of sulfur are rhombic and monoclinic sulfur. Rhombic form is more stable thermodynamically. Rhombic and monoclinic forms undergo reversible changes at 368.5 Kelvin, which is the transition temperature. The S2 molecule is paramagnetic and blue colored like O2 due to presence of unpaired electrons in its anti-bonding p-pi orbitals. Sulfur dioxide. It is prepared when sulfur is burnt in air or oxygen. Industrially, it is produced as a byproduct of the roasting of sulfide ores. In laboratory, it is prepared by the action of sulfuric acid on copper turnings. Structure of sulfur dioxide is similar to that of ozone. It has a bent structure. The resonating structures are shown, which are also similar to that of ozone. Only the position of double bond differs in the structure. Properties. When moist, sulfur dioxide behaves as a reducing agent. It converts iron 3 ions to iron 2 ions and decolorizes acidified potassium permanganate solution, which is a easy test for the gas. Treatment of basic solutions with sulfur dioxide forms sodium sulfate. It is oxidized by halogens to give the sulfuryl halides as shown. Some uses of sulfur and its oxides. Sulfur is obtained from mining, from H2S, from sulfides. It is used for vulcanization of rubber and in pesticides. On heating with oxygen, it forms sulfur dioxide, which is further used to form sulfides, sulfur trioxide, which is ultimately used to form sulfuric acid, an important compound of sulfur. Oxo acids of sulfur. Sulfur forms many oxo acids with different oxidation state. The first one is sulfurous acid, that is H2SO3 with the lone pair on sulfur. Then sulfuric acid, the most common acid, H2SO4. Then peroxo disulfuric acid, H2S2O8, also known as Marshall's acid. And pyrosulfuric acid, H2S2O7, that is oleum. Manufacture of sulfuric acid. The two major processes used in production of H2SO4 are lead chamber process and contact process. Lead chamber process is the older one. In contact process, the first step is oxidation of sulfur to sulfur dioxide. Then sulfur dioxide is changed to sulfur trioxide in presence of catalyst, vanadium pentoxide. This sulfur trioxide is absorbed in 98% H2SO4 to form oleum. Oleum is diluted to give sulfuric acid. The best way to dilute sulfuric acid is to carefully pour the acid into water with stirring and not the other way round. Pure sulfuric acid is colorless, corrosive and oily liquid that boils and decomposes at around 300 degrees centigrade. This is the figure showing contact process for manufacture of sulfuric acid. The flow diagram. Some chemical properties. Being a strong acid, it also shows dehydrating nature. Concentrated acid, when added to sucrose, it produces a spongy mass of carbon, as shown in figure also. Oxidizing nature, it's a powerful oxidizing nature, though intermediate between phosphoric acid and nitric acid. Both metals and non-metals are oxidized by concentrated sulfuric acid, which is reduced to SO2. As shown here, carbon, with carbon it forms carbon dioxide, SO2 and water. With copper it forms copper sulfate and SO2 and water. Some uses of sulfuric acid. It is used in lead acid batteries, in production of fertilizers, to remove oxides from iron and steel before galvanizing or electroplating, in petrochemicals, dyestuffs and detergents. It is used in production of nitroglycerin, which is used as an explosive, but can also be used as a vasodilator, a substance that dilates blood vessels and can be used in the treatment of certain types of heart diseases. That's all for this topic. Thank you.